In this lecture of analog communication, we will determine the relationship between the phase and the frequency modulation. Again, the angle modulated signal St can be given by St is equal to AC cos 2 pi Fct plus Kp into Mt for phase modulation, and St is equal to AC cos 2 pi Fct plus 2 pi Kf integration from 0 to T m tau d tau for frequency modulation. At first, you will understand how to generate frequency modulated signal or FM using the phase modulator, and later we will understand how to generate phase modulated signal or PM using the frequency modulator. For the generation of frequency modulated signal from the phase modulator, the message signal will be the integrated version of mt with respect to tau, or mt is equal to integration from 0 to t m tau d tau. And in the place of Kp of the phase modulator, we must consider 2 pi Kf. Hence, a frequency modulated signal can be generated by first integrating the message signal mt with respect to the time t, then using the resulting signal as input to the phase modulator. A carrier signal Ct is generated from the carrier oscillator, and it is also given as another input to the phase modulator. Graphically, this can be shown as here input to the integrator is the message signal mt, which integrates the message signal mt and generates the integrated version of the message signal mt, or integration from 0 to t m tau d tau, which along with the carrier signal Ct, which is equal to AC cos omega Ct or AC cos 2 pi Fct, is given as another input to the phase modulator, and both generate the frequency modulated signal. Now we know that the output of the phase modulator St is equal to AC cos 2 pi Fct plus Kp into Mt. In the place of message signal Mt, we will put the integrated version of the message signal integration of m tau d tau from 0 to t generated from the integrator block, and the Kp should be considered as 2 pi Kf. Then the output of the phase modulator will become St is equal to AC cos 2 pi Fct plus 2 pi Kf integration from 0 to t m tau d tau. And this is our desired frequency modulated signal. This shows that a phase modulator can in need be used for producing frequency modulation if the message signal mt is integrated and given as message signal to a phase modulator. The output modulated signal will be a frequency modulated signal. In the similar fashion, PM can also be generated from frequency modulator. For this, mt will be differentiated version of original message signal mt with respect to the time t, or mt is equal to dmt by dt, and in the place of 2 pi kf, we must consider kp. Hence, a phase modulated signal can be generated by first differentiating the message signal mt with respect to the time t, then using the resulting signal as input to the frequency modulator. Again, a carrier signal Ct generated from the carrier oscillator is given as another input to the frequency modulator. Graphically, this process can be shown as here input to the differentiator is the original message signal mt, which differentiates the message signal mt and generates the differentiated version of the message signal mt, or dmt by dt. This differentiated version of the message signal dmt by dt along with the carrier signal Ct, which is AC cos omega Ct or AC cos 2 pi Fct, is given as another input to the frequency modulator, and both of them generates the phase modulated signal. We know that the output of the frequency modulator St is equal to AC cos 2 pi Fct plus 2 pi Kf integration from 0 to t m tau d tau. In order to produce the phase modulated signal using the frequency modulator, the message signal from the differentiator block was dmt by dt, and it is given as input to the frequency modulator, and 2 pi f is considered as kp. And then this frequency modulator output will become AC cos 2 pi Fct plus 2 pi Kf into integration from 0 to t dmt by dt into dt. This integration and differentiation of the message signal mt will cancel out each other. So we can write St is equal to AC cos 2 pi Fct plus 2 pi Kf into mt. And again, this 2 pi kf must be considered as kp, so St is equal to AC cos 2 pi Fct plus kp into mt. This is the phase modulated signal. Hence, we can say that we can generate phase modulated signal using the frequency modulator. Modulation indices for frequency and phase modulation. Again, the angle modulated signal St is equal to AC cos 2 pi Fct plus Kp into Mt for phase modulation, and St is equal to AC cos 2 pi Fct plus 2 pi Kf integration from 0 to t m tau d tau for frequency modulation. This angle modulated signal can be simplified as St is equal to AC cos theta it, where instantaneous angle theta it is equal to 2 pi Fc t plus phi t, and message signal Mt is equal to Am cos 2 pi Fmt. Now, according to the previous lecture, phi t is the change in the angle of the modulated signal from its unmodulated value or instantaneous value, and by comparison for phase modulation, this phi t is equal to Kp into Mt, or it is equal to Kp T AM cos 2 pi FM T, and for frequency modulation this phi t is equal to 2 pi kf integration from 0 to T m tau d tau, or 2 pi kf integration from 0 to T am cos 2 pi fm tau into d tau, which will give us 2 pi kf into am divided by 2 pi kf into fm sin 2 pi fm t, or this can be simplified as kf into am divided by fm sin 2 pi fm t. So the phase modulated signal can be written as st is equal to ac cos 2 pi fct plus kp into am cos 2 pi fm t, and the frequency modulated signal can be written as st is equal to ac cos 2 pi fct plus kf into am divided by fm sin 2 pi fm t. So from this, modulation index for the phase modulated signal can be written as beta p is equal to kp into am. The modulation index for the frequency modulated signal can be written as beta f is equal to kf into am divided by fm. If we put this value of beta p and beta f in the equation of phase modulated and frequency modulated signal, then st is equal to ac cos 2 pi fct plus beta p cos 2 pi fm t for phase modulation, and for frequency modulation st will be ac cos 2 pi fct plus beta f sin 2 pi fm t. So the phase modulated signal can be written in two ways, or st is equal to ac cos 2 pi fct plus kp into mt, and st is equal to ac cos 2 pi fct plus beta p into cos 2 pi fmt. Here kp is the phase deviation constant and beta p is the maximum phase deviation. Let's understand this kp and beta p more clearly. Phase deviation constant kp determines how sensitively the phase of the carrier signal responds to the amplitude of the message signal. It is measured in radians per unit amplitude of mt, and if kp is large, even a small amplitude of mt will result in significant phase deviation in the signal. Maximum phase deviation beta p. The maximum phase deviation beta p represents the peak value of the phase shift that the carrier signal undergo due to the message signal. Given that mt varies over time, the maximum phase deviation occurs when mt reaches the maximum value mt max. Mathematically, beta p can be expressed as beta p is equal to kp into mt max. Now, the frequency modulated signal can be also expressed in two ways. Frequency modulated signal can be written as st is equal to ac cos 2 pi fct plus 2 pi kf integration from 0 to T m tau d tau, and st is equal to ac cos 2 pi fct plus beta f sin 2 pi fmt. Here, the kf is the frequency sensitivity and beta f is the peak frequency deviation. Here, kf represents the frequency sensitivity of the modulator and its units in hertz per volt. It determines how much the frequency of the carrier signal varies in response to the amplitude of the modulated signal. Peak frequency deviation represents the maximum phase shift from the carrier frequency due to the amplitude of the message signal. It determines how sensitively the frequency of the carrier signal responds to the amplitude of the message signal. It is measured in hertz. Mathematically, peak frequency deviation, or del f, is equal to kf into mt max, where kf is the frequency sensitivity of the modulator and mt max is the maximum amplitude of the message signal. A larger kf or am, which is the amplitude of the message signal, results in greater peak frequency. It affects the bandwidth of the frequency modulated signal. A higher peak frequency deviation increases the bandwidth. Now let us understand this modulation index beta f for the frequency modulation. The modulation index for the frequency modulation beta f represents the peak frequency deviation to the frequency of the message signal. It indicates the extent of the modulation applied to the carrier signal. It is a dimensionless quantity. The modulation index of FM or beta f is given by del f divided by FM, where del f is the peak frequency deviation and FM is the frequency of the message signal. We know that del f is equal to kf into mt max, and so the modulation index beta f can be written as kf into mt max divided by FM. A low value of beta f or less than 1 indicates the narrowband frequency modulation resulting in a smaller bandwidth. A high value of beta f, which is greater than 1, indicates the wideband frequency modulation leading to a larger bandwidth and better noise immunity. The value of beta affects the number of significant sidebands and consequently the total bandwidth of the frequency modulated signal. We define modulation indices beta p for phase modulation and beta f for frequency modulation as follows. Beta p is equal to kp into maximum of the message signal mt, which is equal to del phi max, and beta f is equal to kf into maximum of the message signal mt divided by fm, which is equal to del f maximum divided by w, where the w represents the bandwidth of the message signal and del phi maximum represents the peak phase deviation for phase modulation, and del f maximum represents the peak frequency deviation for frequency modulation. This concludes our discussion for this lecture. In the event that you have any question regarding this presentation, feel free to post them in the comment section and don't forget to hit the subscribe button. See you in the next one.